Good morning. Happy Tuesday. Let's see here. So we've got, I know you know already, test number 2 is on Thursday. Eek. Exciting. You get to show off everything you know. Uh, that's one way to think of it. I posted a practice document. Of course, it's very long because there's lots of practice for all the different types of scenarios. But today I just want to talk about just these bullet points and kind of focus a little bit on what to expect for the test. Of course, we are going to have an online test, so it'll be very similar to the assignments that you've been working on, right? In terms of, entering answers and things like that. And so, in general, though, I didn't finish my thought. You're not crazy. I just didn't finish it. I don't know. I lost it. I lost it. Uh, what I want to do is I want to focus on the proportion questions, just because that's where we spent the most amount of time, and that's where you've had a lot of time to practice. Okay, so there will be 3 long answer questions. Okay. 2 are going to be a hypothesis test. So a hypothesis test times 2 and a confidence interval times 1. I'm not telling you which one is which, right? But of course we have a 1 sample proportion. Let's see here. Sorry, I've got dirt on my screen. Can't see. There. 1 sample proportion questions. These were introduced. We used all of chapter 5 to introduce 1 sample proportions, and then 6.1 also talks about 1 sample proportions, so just more practice. We kind of skipped 6.1 because we'd spent so long in chapter 5 introducing concepts around hypothesis testing and confidence intervals. Now, the sample size calculation, I'm going to have as a bonus question, because we didn't talk about it explicitly in class. I mentioned it, but we didn't talk about it explicitly, and so I'll use it for a bonus question. You've had questions on it for extra credit on one of the assignments. Can't remember which one, but so you could try those again just for the sample size calculation. 2 sample proportions. Right now it's tricky because we have information from 2 samples, and so then we need to keep track of which sample gave us which information, and usually we want to compare those 2 proportions. Are they significantly different from each other, or is one less than the other, or is one more than the other, which is the same thing? Or we can make a confidence interval for 2 sample proportions, right? Depending on what we're doing, a hypothesis test or a confidence interval, for 1 or 2 sample proportions, the conditions that we check change, right? And so what I'm going to have is I'm going to have a list of all the possible conditions that you'd need to check, and you need to tell me which ones you would need to check in that scenario, right? And so what you're going to need to do is you're going to need to read through the entire question and figure out, do I need to do a hypothesis test or am I doing a confidence interval? And that'll determine what conditions to check. Okay? I'll give you a freebie. We only do a hypothesis test for the chi-square goodness of fit, right? And so, okay, kind of narrows things down, right? We're doing 2 hypothesis tests, and I'll make you do 1 confidence interval. And of course, especially for the confidence interval, you'll have to interpret it right? And so that's an important part of what we're doing here. And so you'll have a text box and you'll type in your interpretation, okay, which we haven't been doing on the assignments because then I'd have to mark them all. That's crazy. That's crazy. I don't want to do that. But on the test, of course, I will. Okay. Same thing for the hypothesis test for your conclusion. Your conclusion is worth 3 marks, usually out of 7 or 8. Okay, so it's a good chunk of your marks. And so that'll also be just a text box where you enter your answer and I read it and I assign you a mark after the fact. Okay, and so there's a lot more marking for me on this test than test 1. Gave myself some freebies on test 1. But now we have to interpret things and draw conclusions. Okay, so then the test will cover these topics. If I'm only focusing on these first 3, then what's up with these last 2? Well, so what I want to do, because especially preparing for the final exam, we need to be able to read questions and figure out what type of question it is, right? Is it one of these types of questions? Okay. Notice how I'm not including the type that we're introducing today, which is kind of the last type of question 2 independent sample means. And that's because I've promised that it's not on the test, but of course it's on the final exam, so might be worth some practice. Save that for your final exam practice though. So for these, all of these, okay, I'm going to have you just read the question blurb, not do any of the problems. So not a confidence interval, not a hypothesis test. Just tell me what type of question it is. And usually what I'll do is I'll get you to tell me if it's a one-sided test or a two-sided test, because I know that that's a kind of a sticking point for a lot of people. And maybe depending on kind of how I'm feeling, uh, maybe I'll get you to pick the right hypotheses. Okay. But that's going to stem from the type of question that you have anyways. And so here, for these, right, tell me the question type and I'll run through it. Um, but roughly 6 of them, okay? I haven't checked it, so I run through it, and then I take my time, and I triple it, and then that's a good length test, and so, so I'm around 6, but we'll see. And 1 or two-sided test. So tell me what type of question it is and if it's a one or two-sided test. Okay. Okay, good. For a tiny bit of review, um, I'm keeping my eye on the chat. If you have any questions about the test, then just put them in the chat. Um, so let's see here. Review. Last week, we started talking about means. So we're analyzing means. Which is numerical data. Oops. Well, this doesn't look like means at all. Potentially more than one, right? We started with one mean and we said, okay, one sample mean. What's the information that I have to give you in a one sample mean type of question? Well, I have to give you the sample mean. I have to give you the sample standard deviation, and I need to give you the sample size. I also need to give you mu naught, the value that we want to compare the sample mean to, right? And that mu naught is going to be what's in your hypotheses, your null and alternative hypotheses. And so for one sample mean, and I'm gonna do them side by side so that we we see the similarities between one sample means and paired samples, so two paired samples. Um, the null hypothesis is that mu is equal to mu naught. I'm not going to write the alternative because it could be less than, it could be greater than, it could be not equal to, but other than that, it's the same as the null hypothesis. And that's the same on your formula sheet, right? And so that's what it says on your formula sheet, is that mu is equal to mu naught, and then the alternative is the same. The only thing that changes here is the sign, and that sign determines if you have a one or a two-sided test. Then step 2, do the test, calculate the test statistic. We take x bar, how far is it from mu naught, from our hypothesized mean, taking into account the standard error, which is s over root n. And then we have n minus 1 degrees of freedom, because if I've calculated a t, I need my degrees of freedom to either use the table or to use software. It doesn't matter. We'll need to have the degrees of freedom, which is n minus 1. Once you have your p-value, whether it's from the table or from software, and in the assignments, I've been making you do both just to see which one you prefer. Uh, and so some people will prefer Excel and some people will prefer the table. And I'll find a way. I haven't figured it out yet. I have to ask Steve, who sits there, how I can have it give you marks either way, but I'll figure it out. So just pick whichever one you're comfortable with, and that'll be good. Okay, so a confidence interval, oops, for the mean, take our point estimate plus minus t star, right? So no longer z star, t star at n minus 1 degrees of freedom. Sometimes we'll put a little subscript n minus 1, but I'm going to drop it, times s over root n. Okay. Now, what we did on Thursday was we said, okay, what if I have two samples? So two samples of numerical data, but it's a special case where those observations are paired, right? So kind of before and after scores, left foot, right foot for shoes, or kind of brand A, brand B for usually the common example is shoes, where we're testing, durability. So then we randomly assign brand A to some foot and brand B to the other foot, and we keep swapping those, but then they're paired across the subject, the person wearing the shoes, because some people might wear out their shoes quicker, right? But then both would wear out fast, and some people might not wear out their shoes very fast at all. Yeah, so the T star we get from the T table. I'll just jump there. Okay, where's it? I'll bring in the tables here. Oh, here's a highlighted one. If I want to make a 95% confidence interval, then you'll go to whatever degrees of freedom you have. Just as an example, let's say you have 100 degrees of freedom, then your T star is going to be 1.984. Nice. And that was from the chat. Okay. So now we have two paired samples. Awesome. This is where we analyze the difference, right? And so thinking about the shoes, how they wear out, right? How we capture the fact that maybe someone wears out their shoes faster, or maybe someone wears out their shoes slower. right, then we take the difference, we calculate the difference. Maybe brand A minus brand B, for example. And so we're analyzing the mean difference. If you've got your formula sheet handy, then you'll see that all I'm writing out is essentially the formula sheet, but together, right? And so it's nice to get to know your formula sheet. The only thing that I don't have on there is this, right? Um, but that's why I did it in light blue instead of dark blue. Okay. So if I have two paired samples, right? So I have two samples in my data. I have brand A and brand B, right? But I have the same individual wearing one of each brand, right? And so then what I do is I calculate the differences in a new column, and then I can ignore all this information. So those two original samples, I drop those, and now I'm analyzing the differences. And I want to know if the difference, so the average difference is different from zero. Very, you have to really stay on top of the terminology there. But all we have is we have a sample mean of the differences, and sometimes I'll put or often I'll put a little subscript diff or a subscript d, depending on how lazy I am, just to indicate that this is the mean of the differences. I can calculate the standard deviation of the differences. I have some number of differences. Yeah. And what we said was, okay, so these, notice how these are all the same, right? It's just we've got the differences now. And instead of having some value that I want to compare my mean to, I want to compare my mean of the differences to zero always. And so that's what makes my null hypothesis. My null hypothesis is always that mu is equal to zero. And then my alternative would be that mu is not equal to zero, right? That's the simplest case. Otherwise, you have to think about how the difference is calculated and how it would relate to being less than zero or greater than zero. That's an assignment type of question where you can really think about it. I wouldn't do that on a test. I would only ask now this is where it gets boggy. If the mean difference is significantly different from zero. Oy. Right? And so, or more simply, is there a significant difference between the two groups, right? And that would be where mu is different from zero. I'm just going to check the formula sheet. I think maybe I have a diff on the mu as well. Just, oops. I think I do. I do. Mu diff equals zero. Just to highlight that it's the difference. Mu diff there. But knowing that now I have this one sample means type of question, it's just that my one sample are differences. So then my t is going to be my sample mean of the differences, technically minus zero, right? How far is it from zero? My hypothesized value of zero. Divided by S diff divided by the square root of N diff. No surprise, the degrees of freedom is going to be N diff minus 1. So number of differences minus 1, and that's on your formula sheet as well, right? And then your confidence interval for the differences for the mean difference. And so what we want to remember is that for the mean difference, the interpretation, we have to be really careful, right? Because a negative difference means that the second value is larger than the first, right? Brand B was larger than brand A, for example. Um, and the positive difference would mean that brand A was larger than brand B if we took A minus B as the difference, right? And so those are all the things that we talked about last day. And but just it's been a whole weekend, so it's worth reminding ourselves. Still T star as our critical value times S diff over root n diff. That's the end of our review, right? So basically we did this on Tuesday, the one sample means, and then we did the same thing over again, just a special case for the paired data, or the matched pairs, sometimes I call them. Okay, so here we said, okay, what if I have two paired samples? So the special case of having paired samples. Then we talk about the mean difference. Okay, so today we're going to introduce the difference in two means. So now I have two independent sample means. And so in terms of the type, I'm going to call it two independent sample means. Oops. And this is section 7.3. This is going to be our last section in chapter 7. I'll post a bonus assignment, right? An opportunity to boost your assignment grade if you're missing one or have a low one, but you don't have to do it if you don't want to, where we go into, well, what if I have 3 or more means, right? Then we use what's called an ANOVA, okay? But we'll save that for a second course in statistics, the classic cop-out. Not for this course, not for us. Okay. So, difference in two means. Well, first of all, let's talk about, well, in order to have two means, now I'm going to have two samples of numerical data that's not paired, but these samples are independent of each other. I'll put in brackets not paired, independent of each other. For example, maybe city A and city B. Something like that, right? I've got group 1, group 2. There's no natural linkages happening. Hey, balloons. And that's okay. It's actually the most common t-test that we do. So often when we're calculating a t in our hypothesis test, we just call it a t-test a t-test to sound cool, I guess. And so it's the most common t-test that we do, is just two independent sample means, right? If I want to compare the grades in our class to the grades in Steve's class, right, then there's no way to say that, oh, this student links to this student, and we don't need to do that, right? We can just say, well, they're two independent groups. I'm just going to analyze those means, right? Those average grades, are they significantly different from each other? Right. And so that's something that that the college absolutely analyzes, right, to see, okay, was there a significant difference in the grades here? It's something that I analyze personally, right? If I have in my written exam questions, I always have a version 1 and a version 2, and I want to know, okay, was there a significant difference in the grades? There never is, but I'm concerned about that, right? Because if one version was harder than the other, then that's really, really bad, right? They're like basically the same, so it's not a problem, but it is an analysis that I do. So usually we have these two independent sample means that we want to compare. Now, the problem is that we're going to have sample 1 and we're going to have sample 2. Just as before, we saw this scenario with proportions as well, right? We're going to have some X bar, we're going to have some sample standard deviation, and we're going to have some sample size. But we're going to have it for each sample. Notice that all these things, right, they're the same things that I listed earlier for the one sample means. Okay? And so here we're going to have x1 bar, x2 bar, s1, n1, s2, n2. So of course our formulas have to take this into account, okay? And maybe what I'll do, just to introduce the concept a little bit further, I'll put this on the next page here. Give myself some room. The point estimate is always going to be x1 bar minus x2 bar, or x2 bar minus x1 bar, but because we're just using ones and twos, you can assign whichever group you want to whichever value. And so x1 bar minus x2 bar, right? The difference in the means. So now we're analyzing the difference in means as opposed to going back to the paired data, as opposed to the mean difference. Okay. Very subtle differences, haha, there. And so you have to be really, really careful. Okay? What's nice is that the standard error of x1 bar minus x2 bar is always going to be this, regardless of the confidence interval or the hypothesis test, right? And so the standard error is going to be s1 squared, over n1 plus s2 squared over n2 square rooted. Why is that nice? Well, because if I want to do a hypothesis test, my test statistic, t, is the point estimate, minus the hypothesized value, which we don't know yet, but I think you can get there, over the standard error of the point estimate. So we're still going to calculate a t, right? And we're still going to calculate a confidence interval. A confidence interval is always the point estimate plus minus some critical value, which I'll just write CB, times the standard error of the point estimate. And that's why it's so nice that the standard error of the point estimate is always the square root of s1 squared over n1 plus s2 squared over n2. It's long and tedious, but it's not hard. This is the standard error. Oops. I'll use the same abbreviation that I did down here, right? So now we can go to our formula sheet and have a look. Oops. Nope. The formula sheet is bigger because we have more information, but besides that, nothing crazy is going on here, right? Again, this distribution from the central limit theorem, that's just theoretical, so you can kind of scratch that out and ignore it. It's what we're using later on. So we can make a confidence interval for the difference of the means, okay, mu1 minus mu2. Well, here's our point estimate. Here's my critical value, which is a t star, and then my standard error is s1 squared over n1 plus s2 squared over n2, square rooted. For a hypothesis test around mu1 minus mu2, which is the difference in the means, the difference of two means, right? And so here I'm going to use this version. Mu1 minus mu2 is equal to 0, but in the same way that we had for the proportions, we could also write it mu1 equals mu2, which kind of condenses it a little bit. But the reason that I like mu1 minus mu2 is equal to 0 is because our point estimate, right, up in the t here is x1 bar minus x2 bar, technically minus 0, right? My null hypothesized difference in the means is 0. Okay? And so here, the hypothesized value is going to be that mu1 minus mu2 is equal to 0. And so this is always 0. How far is the observed difference from 0? Same idea as what we were just doing, right? And then over the standard error of the point estimate, which is the same. Now, the only tricky part is the degrees of freedom we are going to use. Now, there's a huge formula, right, that we could use that software uses, but we're not going to use that because that's crazy. We're going to use the smaller sample size minus 1, okay? And so reading this here, it has the minimum function, which takes the minimum of 2 values or more, in our case 2, so n1 minus 1 or n2 minus 1. And so here, right, the degrees of freedom is the smaller sample size minus 1. This gives us a conservative estimate for the degrees of freedom, and that's totally fine. Okay. I think we're ready for an example. Let me check the time. Okay. So our example is about diamonds. And so in case you are unaware, weights of diamonds are measured in carats. So 1 carat, we're going to call it 100 points, and 0.99 carats is going to be 99 points. And that's just to bring it to some scale that we can work with. Okay, and so some kind of fun facts: the difference between the size of a 0.99 carat diamond and a 1 carat diamond is undetectable to the naked human eye. I don't think we need to say naked, we can just say human eye, I think. But what we're interested in, well, does the price of a 1 carat diamond tend to be higher than the price of a 0.99 carat diamond? If it is, then I would say, well, why don't you just go for a 0.99 carat diamond if the price is significantly less? Okay? And so, let's see here. Oh, this is the part that I was scrolling through the notes, and I was like, there's something I don't like in here. There's something that bothers me in here. It says we're going to test to see if there's a difference between the average prices. We can do that. That's a two-sided test, right? But I think, let me just go back here. Yeah, I'm just gonna scratch that because later, that's what it is. Later, we actually do test to see if the 1 carat diamonds tend to have a higher price than the 0.99 carat diamonds, so just ignore that. So just some background information, right? So in order to be able to compare equivalent units, what they've done is they've taken the prices of 0.99 carat diamonds and divided by 99, and 1 carat diamonds and divided by 100, and then we're comparing the average point prices, so the average price per point, right? And so depending on if you have a 0.99 or a 1 carat diamond, it'll be 99 points or 100. And so, that's just extra information, we don't need to worry about that, um, it'll just be given to us anyways. So, here, side-by-side box plot, um, we have the point prices, right, of a 0.99 carat diamond and a 1 carat diamond. Okay. We have a sample mean for each sample, right? And one of the things I want you to notice is that the sample sizes are allowed to be different. Okay. And so here, notice we allow different sample sizes. That's kind of cool, I think. Right? We can have different sample sizes and we can still compare the means of each group. And so here, in terms of um, X bar, let's say 99, right? Could be X1 bar, X2 bar. Um, S99, S1, kind of confusing, 100, I guess, and 99 and 100. All right, if we make it question specific. Okay, so what we said was, all right, we're going to be talking about the difference in the means. So the difference in these two means. So the parameter that we're interested in is the average difference between the point prices of all 0.99 carat diamonds and 1 carat diamonds, right? And so this is what we're really interested in. But what we have, our best guess, our point estimate, is the sample mean of the 99 carat diamond or 0.99 carat diamonds. Oh my gosh. And the sample mean of the 100 point diamonds. Okay. And so our hypotheses for what we want to test, and what I'm going to do is I'm going to add a page here. Let me just scroll ahead just briefly here. We're just going to go ahead and do this one together. So here, I'll alter the question a little bit to, is there evidence the average point price of 1 carat diamonds is higher than the average point price of 0.99 carat diamonds? So I'm changing it a little bit. Notice the is there evidence? That's going to be our biggest clue that we have to do a hypothesis test. And so for step 1, state the hypotheses. Remembering the order, so it gets a little bit weird here. Because I have the information like this, and because I know my brain doesn't want to do subtraction, it just doesn't want to work from right to left. It just, I don't know, I can't do it. It doesn't matter which one you assign to group 1 and group 2 as long as you're consistent, right? And so here, we're talking about 1 carat diamonds and 0.99 carat diamonds, but really we want to know if this one is higher than this one. Looking at these values, 53.43 is higher than 44.5. We want to know if it's significantly higher. And so our hypotheses are going to look like this. Mu of, and I'll use 0.99 minus mu 100. Well, I have to assume that they're the same until I have proof otherwise. So my alternative hypothesis is going to be mu 0.99 minus mu 100. How's it going to relate to 0? So I still have to talk about how it relates to 0, but this is one of those tricky ones where we have to think about it a little bit. If I want to know if the 1 carat diamonds are higher, right, and I'm taking 0.99 minus 100, if this value is higher, then subtracting a larger number from a smaller number, 1 minus 2, for example, right, gets me to -1, and that's less than 0, and that's always going to be the case. And so that difference, less than 0. This is the reason it's a one-sided test, or one-tailed test, if you prefer. Okay, we don't need that until step 3 where we find the p-value, but we do need to make a note of it, or it's helpful to make a note of it. I'll mention the conditions. I haven't talked about them, and that's just because they're the same as for the one sample means, and they're relatively simple compared to proportions. So, what are the conditions? Independence. I have to have randomly sampled my 2 samples, and they have to be independent of each other. That's new from the paired data, right? So randomly sampling. And I don't think it said explicitly, but there was a footnote saying these data are a random sample from the diamonds data set in the ggplot2 R package. Now we're not using R, so don't worry about that, but it's just a data set. Randomly sampling ensures observations within each sample are independent and that our 2 samples are independent of each other. And so here, independence within, but then we also need it between for 2 independent samples. 0.99 carat diamonds are independent of 1 carat diamonds. Of 1 carat diamonds. That's the independence condition. And then the normality condition, how do we check it? Well, we need a sample size larger than 30 in each group. I don't have that. I have 30 here, but I only have 23 in the 0.99 carat diamond group. So what do I have to assume? I have to assume that they're relatively normally distributed. Now we're given the box plots, so we could say, well, it looks relatively symmetric around the median, so then I can assume normality. You won't have that on the test, and so I'm not too worried about it. Or on the final exam, I guess, is when we would see this stuff. And so normality n for 100 is larger than or equal to 30. So we can assume normality. N of 0.99 or 99, I guess. Be consistent, Emily. I haven't been. Is 23, which is not less than or greater than 30, so we have to assume normality. But we assume the distribution is approximately normal. The distribution is approximately normal. So you either have a sample size greater than 30 and then you can assume normality, or if you have a sample size less than 30, then you just have to assume normality, right? Either way, the normality condition will be met. Okay, now we're ready for step 2. Do the test or calculate the test statistic. T is x1 bar minus x2 bar. I'll write the generic formula out first. Technically minus mu1 minus mu2, assuming the null hypothesis is true, so this will always be 0, right? Since we just said that our null hypothesis is that mu1 minus mu2 is equal to 0. So I don't even write that, usually. Over the square root of s1 squared over n1 plus s2 squared over n2. That page, oops. Okay. Do I have? Nice. Just put my information there. As long as usually if you're using just question-specific subscripts in your hypotheses, establishing which one is group 1 and group 2, it gets really annoying and boggy to use question-specific subscripts in your T, so I don't. I tend to just use the generic subscripts, but I'm going to call this group 1 and group 2. Right. Then I can just plug those values in. So now I have T is 44.50 minus 53.43 minus 0 technically, divided by the square root of 13.32 squared. Now that's new, right? Because usually we have s over root n, right? But if we think about, okay, now my square root is on the outside, and if I illegally distributed my square root, right, because we have addition here, so we can't do that, but if I did, then this would become s, and then the root n in the bottom would just be, oops, the same as before, over 23 plus 12.22 squared over 30. So these squares, those are the ones that people love to forget about because they're kind of new to us. We're not used to seeing it like that. Okay, so now I'm going to calculate this, clear all, and let's see here. I'll put it in brackets, 44.5 minus 53.43. That's the difference in the means. My point estimate for the difference in the means. I'm not going to put the minus, well, okay, fine, I will. I can't resist. No, I won't actually, because it messes. I should have had more brackets, but I'm finding it hard to click in there. So now, in my denominator, I need to have the square root, and I want to make sure that everything stays in the square root, and just making sure that everything looks how I want it to, especially when you're working on your calculator, right? You'll want to be really careful with how you enter values. And so what I would be doing is I would be taking this first value, squaring it, dividing by n1, maybe storing it in your calculator, putting it away for a rainy day, and then deal with this one individually, kind of pick away at them, add them together, take the square root, Usually people forget to take the square root and then divide by the numerator. So now here we go. I'll put a bracket, 13.32 squared divided by 23. I don't think I need those brackets. Let's see here. Divided by 12.22 squared. Okay. To clean it up a little bit, I'll ditch these brackets there. Divided by 30. I think that's good. I'll screenshot that and bring it in so we can oops. Yeah. At this point, it might be nice to have something generic set up in Excel, right, that you could use for the test and for the final exam, right? Where what are you changing? You've got, right? You've got essentially an Excel spreadsheet where all you have to do is change your means and your standard deviations and your sample sizes. And then as long as you're referencing cells, right, in here, then it'll just do it for you, right? That pleasing, will just do it for you. Then, so our t is roughly negative 2.5066. I did 4 decimal places, doesn't really matter. The table, if you're using the table, it has 3 decimal places, so you want to have at least 3 decimal places. Now, step 3. Find the p-value. Gut reaction, though, right? What does this mean? It means that the difference that we saw, and I don't have it explicitly, but 44.5 minus 53.43, is it just, yeah, is 2.5 standard errors away from 0. If, in fact, it's below 0, right? And so that means that it's quite far away, using kind of 2 as a threshold in either direction. And so my gut reaction is that I'm probably going to reject H naught, right? But we'll use the p-value to make that decision. And so here, because I have a t, the setup that we use is using the t-table with now our degrees of freedom calculation. This is the first time that we're seeing it, and so I'll do it down here. The degrees of freedom is the minimum of n1 minus 1 or n2 minus 1. In our case, this is going to be the minimum of 23 minus 1 or 30 minus 1. So I'm going to do those calculations inside that minimum function. And so I want the minimum of 22 or 29. Well, the minimum of 22 or 29 is 22. So that's how we are going to find the degrees of freedom. There are other methods, but I want you to use this one, okay? Because otherwise, that's how the questions are programmed. And so the other option is to take the 2 sample sizes, add them up, and subtract 2. But I don't want you to do that. So if you're watching a video where they do that, just remember that I want you to use this one. It's a more conservative estimate, and that's why we use it. Okay, so I have 22 degrees of freedom. Same thing as before. If my degrees of freedom were off the table, so not exactly listed, then I would need to round down, right? And so here, let's see, where's my table? I have 22 degrees of freedom. Okay. And let's see here. Copy. I'm going to try to put it in the same screenshot here. Let's put it up here temporarily. Sorry. Copy, delete. Just so I don't have to do it twice. Paste image. So I have 22 degrees of freedom, and I kind of scrolled through, skipped a bunch here. And so now I either have a one-sided p-value or a two-sided p-value, and that's where I need to refer back to my alternative hypothesis. Up here, well, I want to know if the difference is significantly less than 0, making it a one-sided test, right? And so I need a one-sided p-value. So I'll highlight that here. Okay. And then what do? I take the absolute value of t, and how I set this up on my page is I find the absolute value of t equal to negative 2.5066 is between two values at 22 degrees of freedom. So 2.5066, I go out here further and further out into the tail until I am between these two values, 2.183 and 2.508. Kind of a tricky one, I think. Because I have to remind myself that 2.507 is less than 508. But besides that, I'm between these two values, 2.508. So my p-value is somewhere between 0.01 and 0.02, remembering that as you move further into the tail, the area in the tail gets smaller and smaller and smaller, and so we have to read them from smallest to largest because of how I have the sign here. So the one-sided p-value is between 0.01 and 0.02. You can use Excel to find the exact p-value, but it'll be somewhere between 0.01 and 0.02. Okay. Last step, biggest step, step 4 is our conclusion. Same 3 things that we have to talk about. I have to compare my p-value to the alpha level. Now, we weren't given an alpha level, so I'm going to use 0.05. I'm going to assume it's 0.05. That's the default. And then what does that mean in terms of the null hypothesis? And then, of course, what does it mean in terms of the question? So, same format as before. Since the one-sided p-value is between 0.01 and 0.02, those are both less than 0.05. And if it helps to draw a number line, then go ahead and do that, right? But you can also, if you want, as kind of a guide, you could also say, well, 0.05 is here and I'm further out into the tail, so it's less than 0.05. That's an alternative way of looking at it. And so it is less than our assumed alpha level of 0.05, which means we have enough evidence to reject H naught. Which means we have enough evidence to reject H naught. And if I'm rejecting it, then I should probably say in favor of what? In favor of the alternative hypothesis, in favor of HA. And then, of course, in terms of the question, so now, therefore, I'm just going to copy the question, which we condensed a little bit. Whoops, there. Copy. Therefore, I'll do this. There is evidence that the average point price of 1 carat diamonds is higher than the average point price of 0.99 carat diamonds. Oops, period. Right? That's what that means. If I reject H naught, then that's what that means. Now, a common follow-up question then would be what? Okay, so I've established that the point prices are of 1 carat diamonds are significantly higher than 0.99 carat diamonds. The follow-up question might be how much more, right? And so then we do a confidence interval. Okay. And so here, the next step is to determine how much more the 1 carat diamonds are per point than 0.99 carat diamonds. We use a confidence interval. Let's make a 95% confidence interval for the difference in the mean point prices. So the question might be, and maybe I have it, maybe let's give me a quick brief moment here to skip through and see. Da-da-da-da-da-da-da. Okay, not exactly. I'll just do it myself. If you want something done right, do it yourself. All right. Construct a 95% confidence interval. Oops. For the difference in the mean point prices. Okay. I want to make a 95% confidence interval. I'm going to recycle a lot of the information that we already had, right? And so we know the standard error, which you've already calculated. We did it in Desmos, but you would have it somewhere and probably stored in your calculator or in Excel or something like that. So then you can just reuse it if you want, right? And so what we have, we want to build a confidence interval for x1 bar minus x2 bar plus minus t star times the square root of s1 squared over n1 plus s2 squared over n2. Yeah. The only thing that's new here is the t star, and t star at 22 degrees of freedom. So the degrees of freedom stays the same. T star for a 95% confidence interval. So notice how I use the little 22 down here. That's just the degrees of freedom. So from our table, maybe now what I'll do is I'll do the same thing. Copy, but bump it up here. Bump it up. Copy. Need more room. I'll just do this. So if I want to make a 95% confidence interval at 22 degrees of freedom, then I have a T star of 2.074. Add a page. Okay. All the other components I already have, right? So I'm just going to use Desmos and switcheroo some things here. Oops. Can I copy this? Minus 2.074, I think. Yeah. 0.74 times that. Throw some brackets up around here, why not? Didn't change anything. So that's my lower bound. Then can I copy this all? Fine. I should have stored it, but 4.3 plus 2.074. Now hopefully I don't make a terrible typo here. 13.32 squared divided by 23. Bump it up plus 12.22. Oops, not square root, it's squared. Divided by 30. Okay, good. Looks good. Assuming the previous one was good. I'll bring that in so we can see it. So again, if you've set up a clever Excel spreadsheet, right, then you could have it referencing the different information, and then you could just have it generate the confidence interval relatively easily. Right? And that goes for all these questions, right? There's things that we need to know, and you plug those in, and then it'll just do it. So now our interval, negatives are tricky, right? Because the larger values are actually smaller, right? Because you're moving away from 0. And so now when we write this interval, so the confidence interval is between negative 16.32, because why did I go to 2 decimal places? Because it's money, right? And so it's a difference of 1632 up to a difference of negative $1.54 per point. All right, so these are the differences per point. Remembering that a 1 carat diamond has 100 points, right? And a 99 or a 99 carat or 0.99 carat diamond has 99 points, right? And so these are the per point prices, right? And the differences are consistently negative, which matches our conclusion before, right? Because if the difference was 0, then there would be no significant difference, right? But we found that there was in fact a significant difference, and the difference was significantly less than 0, right? Only because of how we've calculated the difference. Now it's time to interpret this. We use the same interpretation as always for the confidence interval. We are 95% confident, right? That's always our start, 99, whatever you made. The interval from negative $16.32 to negative $1.54 captures the difference in the mean point prices. The difference in the mean point prices between 0.99 and 1.00 carat diamonds. I'd say a difference of $16, right, which is at the very maximum difference, right, that we could have per point is quite large, right? Maybe $1.54 per point isn't that big of a difference. Then you can say that you got a 1 carat diamond. Maybe that's worth it to you, right? But what we're saying is that the true difference, so the population difference in the averages, is captured somewhere in this interval. You can take this further and say that, okay, a difference of negative 1632 is the same as saying that the 1 carat diamond is $1632 higher on average than the 0.99 carat diamonds, but that's not something that I expect you to do. Right, I want you to be able to find the interval, that's important, and then interpret the interval, but you can just take it at face value. So we're some percentage confident that the interval from here to here, whatever you found, captures, and then whatever I asked you to build a confidence interval about the mean, the difference in the mean point prices in this case. Yeah. And so that's the layout of the hypothesis testing is, okay, we establish that one is different from the other, right? And then the confidence interval is a follow-up typically where we say, okay, well, how different, right? Knowing that they're different is not usually going to satisfy anyone. Then we have a follow-up of, okay, well, how different are they? Okay. Nice. So we did these all together. I'll keep the slides in here when I post the notes, but we did all of this. Ba, 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 ba. Oy, 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 oy. Just want to make sure that you got it. Mm. Oh yeah, here for your conclusion. Now, as statisticians, it's not really our job to make recommendations. All we do is analyze stuff. And so that's what frustrates people the most is they hire us, me, to do this work. And I say, yes, there's a significant difference and this one's more expensive than the others. And then they want me to go on and say, which one would you choose? And that's not my job. My job is just to establish that there is a difference and here is the difference, right? And so, but what could we use it for? We're going to reject H0, and so the data here that we have provide convincing evidence to suggest that the point price of 0.99 carat diamonds is lower than the point price of 1 carat diamonds on average, right? So what can we do? Well, I maybe buy a 0.99 carat diamond. It looks like a 1 carat diamond, but it's significantly cheaper, right? And so that's kind of the take home, or really whatever spin you want to put on it. Go for it. That's not my job. When we made our one-sided hypothesis test centered on 0, we found a t here. T was negative 2.5066. And we used an alpha level of 0.05. So we put all our alpha equal to 0.05 down here in this tail, right? Now, the thing about one-sided tests versus two-sided tests, so one-sided tests put all the alpha in 0.05 here. And so what would we need to do? I would need to make a confidence interval, I would also need to put 0.05 up here. Yeah. And so really, if I'm using 0.05 as an alpha level for a one-sided test, I'm going to have to use the 90% confidence interval And I guess I could highlight it here. Right, because then I would have 90% here. That's not something that we need to worry about, but it is something, kind of interesting in linking the two. Right. Uh, well, we did that. We found the confidence interval. There. Just didn't want to miss anything. So 7.5, we're actually skipping 7.4. 7.5, 7.4, we skip completely. We're skipping 7.5 as well. And so review on your own, which means it'll be a bonus assignment. But it's not tested, right? So it won't be on the final exam, but you'll have a bonus assignment, try to boost your grades, and that'll be good. But all we're doing with an ANOVA is we're comparing, well, what if I have more than 2 means, right? 3 or more means, then is there a difference between these means? And we'll end there. If you have any questions, let me know. Otherwise, test day on Thursday. I guess I should say that. I'll be here, but you don't have to be in the Zoom room. I'll add that to our notes, actually. I forgot completely about that. I will be in the Zoom room. If you have questions. Oops. But same as test 1, you don't have to be there. But I'll be here hanging out if you have a question. All right. There we go. Now I'll end this recording.